Good morning, everyone. Welcome to the class. So far in this semester, I was talking about signal line design, especially if if you want to send very high-speed digital signals, the structure should be a transmission line. When we are designing transmission line, we have to control the impedance as well as termination impedances. Also, we want to minimize the loss, and usually the loss is creating the ISI problem and jitter and eye diagram distortions. In order to overcome that ISI problem, we can add preemphasis and equalizer circuits. Also, I want to remind you that in order to maintain the ground plane and virtual ground plane and impedance, sometimes it is beneficial to use the differential signaling. When we are using differential signaling, we have to control the common mode deflections as well. In addition to that, in our class, we was talking about power network design. So we wanted to minimize the impedance. Also, we have to control the resonances. And the PDN impedance has the inductive part and capacitive part and resistance part. We want to add some capacitance, but we want to minimize the inductance and resistance. And depending on frequency ranges, sometimes we are adding decoupling capacitors at the PCB level. Sometimes we are adding decoupling capacitors at the package level and on-chip level, depending on frequency range. In this week, now I would like to talk about ground. In high-speed digital signal, correct name of ground could be return current paths. Signal also need return current path, and power also need return current path. To secure impedance matching and to minimize the reflections, we need solid return current paths. Also, when we are designing power distribution network, we want to minimize the impedance and we want to control the power network resonances. In those cases also, we have to secure return current path. So final design of our high-speed digital system will be on return current path. And in other words, return current path can be named as ground. So today and Wednesday, I'm going to talk about basic understanding and physics associated with return current path. Now, I would like to excite some imaginations of students. I'd like to give you some cases in which we have a different return current path. Sometimes we have a signal return current path and power ground path, return current path. Also, signal and power ground paths might be separated, as sometimes they are on the same metal plane. Also, I would like to say return current path changes depending on decoupling capacitor positions and also depending on whether you are charging I/O lines or you are discharging the I/O lines. So I will give you some cases right now, and please pay attention. Even though in the textbook we are not saying anything about ground, ground is the really important part of our interconnection design. So there are many difficult parts of the ground design. I would like to show you some examples today. In this case, I would like to discuss about the return current path for the charging case. Here we have an I/O line, and between signal line and multilayer PCB and ground, we have some capacitance. Of course, we also have inductance and resistance, but at this moment, we are assuming that we are only concentrating for the case that I/O interconnection can be modeled as a capacitance. Those cases could be true when interconnection line length is very small, but general understanding of return current path at this moment will be okay for this capacitive loading. In addition to that, this CMOS I/O driver, we have to supply the charge. Power is connected to I/O driver, and ground is also connected to ground plane. And in this case, power ground plane and signal ground plane is connected. In this case of digital circuit, we have a signal return current path and power ground return current path. And return current path, we may have return current path that is digital ground. In the digital interconnection system design and digital circuit, definition of digital ground means return current path. Sometimes in multilayer PCB, we are saying that is reference plane. Please forget about the definition of ground in the conventional analog circuit design. Please forget that definition of digital ground is return current path. And sometimes we call it as a digital ground, and sometimes we call it as a reference plane. So in order to understand the digital ground and properly to design the digital ground, we have to be able to figure out return current path. Now, what I'm trying to do with my students at this moment is to define a return current path, and I want to like to give you some examples. In this specific case, we are sending I/O current to the signal line at a PCB, and return current is actually coming back to the through the ground signal return current path. Usually signal line and ground line are facing each other, and there are certain rules of distance and width, and to make it a 15 ohm transmission line. This positively going signal current will give you supply for plus charge at the I/O capacitance, and this return current through this signal return current path is gonna supply the negative charge at this capacitance. When we are sending this plus charge and minus charge to I/O capacitance, we call it as a charging process, and voltage level at the signal line go from 0 level to high level through a transition. So in order to bring the signal line from 0 to 1 level, we have to supply the charge, plus charge, through the signal line, and also we have to supply negative charge to the capacitor through this return current ground signal return ground path. So this method will be called as digital ground. That is definition of digital ground. Meanwhile, this plus charge and current has to be supplied from decoupling capacitors. This decoupling capacitor could be placed at on-chip level or package level or PCB level, depending on different frequency ranges. Different frequency capacitance charge will be supplied to the CMOS driver. In some case, discharge will travel at the speed of light, and because of the reflections at the end of this power ground plane and decoupling capacitor itself, sometimes we can see the resonances. Anyhow, discharge will be conducted through the power current line, and we usually call this power supply network. At the same way, return current, which is going to flow through the return current path, and this could be called as power ground, probably digital power ground. Because when we are sending charge to the plus charge to the decoupling to the IO driver, that actually go through these PMOS strangers, and that will be traveled to the IO capacitance, and minus charge will be stored at the decoupling capacitance, and that charge will be conducted through the ground plane, and eventually it will be charged to the IO capacitance. So in this is a case for charging. Charging means IO signal have transition from 0 to 1. But interesting thing I would like to emphasize at this moment is that we're gonna have signal return current path, and that will provide the path for return current of signal, and also we're gonna have power return current path. Two separate paths. For the case of signal ground return current path, they will face the signal line in a form of microstream line, and we're gonna design the width and height and dielectric constant to make a 50 ohm transmission line. But however, in this case, we wanna have very wide power line and wide ground line, and dielectric constant could be very high, and H will be as thin as possible because we want to make impedance as small as possible. Here we want to make impedance 50 ohm. So when you are designing distal interconnection and decoupling capacitors, my point is at this moment is that you have to secure good connection of power ground plane and signal ground plane, and they have to be connected. Otherwise, this current has to come back to the decoupling capacitor, negative terminal of decoupling capacitor, and that could be disconnected. So you may be very careful about connection of power line and CMOS transistors and IO lines. In a similar way, you have to secure continuity of ground return current, signal return current, and power return current. This is a special case for a charging case where they have a positive transitions. If you have discharging process, that is gonna be a case when you have transition from high to low level, or depending on position of your decoupling capacitors, this diagram will be totally different. So your job descriptions for different configurations and different state of logic transition, you may have different stories. That's one of the difficulties of ground design in a distal circuit system. At this moment, my point is that in your circuit class, we usually talk about this part and little bit of decoupling capacitance and IO capacitance, but we rarely discuss about this return current and return current paths and this continuity of return current paths. So today and Wednesday, our class will be majorly focused on the return current path. Right now, I was discussing a case where we have a transition from 0 to 1. Now, we would like to discuss a case of discharging process. There, we're going to have a transition from high to low level. So now, I would like to talk about discharging process case where we're going to have transition from high to low level. We have a signal line. We have signal line, and we have ground line, and we are assuming that we have positive charge are charged up at I/O capacitance, and negative charge is stored at the capacitance. When this transistor, NMOS transistor, is turned on, this level of signal I/O will have transition from high to 0 level by turning on these NMOS transistors. NMOS transistor may have certain resistance, and when we are having discharging process, positive charge that was stored at I/O capacitor will move on back to the driver, and minus charge will travel to the back to the NMOS driver as well. So this return current actually will go to the opposite direction. And this arrow means the minus charge is moving to the NMOS driver. And by combining this positive and negative charge, we're gonna generate the heat. That's why CMOS has higher temperature. So in this case, this metal plane, which are facing the signal line to make a 50 ohm, on this plane is gonna be a return current path for discharging current. However, in this discharging process, we do not have any current at the power line and ground return current. We only return current for signal line, because decoupling capacitor has nothing to do with this discharging process, because there's no charge sharing process. So only positive charge charges stored at I/O capacitance could be combined together at the NMOS transistor, and that will create the heat. So in the previous case, in addition to signal line, we had power line, a power current. Because of that, we have ground return current and power return current. But in this discharging process, we only have signal current and signal return current. And in this case, decoupling capacitor has no role to contribute to this discharging process. Second meaning of in this slide, in the first slide, I was saying that because in the charging process, we're gonna have signal current and power current. Because of that, we're gonna have signal return current and power return current. But in this case of discharging process, we do not have power current and power return current. Only we have signal current and signal return current. So my point is that depending on charging or discharging, or where you have decoupling capacitors, and the return current will have different stories. So for each case, different cases, we have to be able to figure out the return current at the power line as well as the signal line. And one typical part of return current design is that especially for the case of power return current, and return current path will change depending on frequencies. As I mentioned many times in the previous classes, power supply network will be different depending on frequency ranges. At a high frequency ranges, probably on-chip decoupling capacitor will be responsible for low impedance. At the package level, probably 100 gigahertz range, we're gonna have some charging current path, and kilohertz range probably on PCB or megahertz on PCB decoupling capacitor will be responsible for charging. So for each different frequency ranges, because of different decoupling capacitor, return current path will be different. So difficult path number one, and return current path will have two different components: signal return current, and power return current. And also, depending on charging and discharging, we're gonna have different return current paths. And also, depending on frequency ranges, we're gonna have different return current paths. And this should be considered for all I/O cases. For example, HBM has more than 1024 I/Os. For all those 1024 cases, we have to do this analysis. And if you have 100 decoupling capacitors, you also have to secure the return current paths for each 100 decoupling capacitors. So this is very complicated because we're gonna have 1,000 I/Os, and also the path will be different for different frequency ranges, and also the return current path will be different for each charging and discharging cases. So by multiplying for all those cases, we may have to consider 10 times cases or million times cases. That's a difficult part of the ground design. Now let's move on a little bit complicated cases. Now we have a power line in the multi-layer PCB. Now assuming our I/O has more capacitance to the power line. Let's assume that we have multi-layer PCB, we have power plane, and we may have signal line adjacent to power, and we may have some signal lines, and then let's assume we have ground. So in the case of signal line on plane S1, there are majorly facing capacitor to the power. In this case, this is gonna be a return power plane is actually serving as a return current path, and this is actually becoming reference plane, and this is actually becoming distal ground. Return current can flow any metal surface, on any metal surface. Human being named it as power, signal, or ground, but Maxwell equation does not understanding human language. As far as their capacitance is stronger, return current will come back through that line. Let's consider a case when we have a transition from high to low level. Then before to make this signal line voltage is gonna change from high to zero level, then means minus charge has to supply to this I/O signal, and that charge will be supplied from the decoupling capacitors. Because this is negative charge in terms of current direction, return current has to go through this line. And then this is actually signal current. Return current actually is going through this power line that will supply the plus charge that will come from decoupling capacitors. So in this case, power current actually that is connected to decoupling capacitor is conducted onto the power line, Meanwhile, current return current is also conducted at the same metal line. For the case of return current for decoupling capacitors, the return current is conducted through the power return current. Very, very typical part of this argument is that we're gonna have power current on the power plane, but power return current is conducted through the distal ground. But we have signal line that is on the negative direction for the case of discharging, and return current for this signal line is actually conducted to power line. No return current is on the ground line. It means that we have separated power return current, signal and power return current. Here, power return current is conducted through the ground metal plane on here, but signal return current is actually conducted through the power plane because major I/O capacitance is between the power and signal. So power plane is serving as a signal return current path. However, this is a little bit complicated. That is very typical part of the ground design. Junyoung, can you shortly summarize this slide for me?
네, 교수님. 전 케이스에서는 이제 트랜지션이 1에서 0으로 일어날 때 시그널 이제 시그널 리턴 커런트 패스로 이제 리턴 커런트가 흘러가는데 이렇게 파워하고 시그널이 커플링 가까이에서 이제 커플링 되어 있는 경우에는 이 리턴 커런트 패스가 저희가 원하는 방향으로 가지 않고 파워 라인에 이제 리턴 커런트가 이제 흐르게 되는 현상이 있다고 말씀해 주셨습니다.
네, 그래서 내 포인트는 우리가 생각하는 그라운드하고 회로에서 그라운드하고 디지털 그라운드는 완전히 다르다. 디지털 그라운드는 우리가 시그널이나 파워를 보낼 때 전류가 돌아오는 길인데 시그널 라인을 예로 들면 리턴 커런트가 꼭 우리가 생각하는 그라운드로 돌아오지 않는다. 파워 라인을 타고 올 수도 있다. 차징이냐 디스차징하냐에 따라서 또는 I/O 라인이 어디에 가까이 붙어서 55ohm을 만드냐에 따라서. 네, 알겠죠?
네, 교수님.
네. The major strong point will be summarized like that. Number one, definition of ground is return current path. Number two, depending on your structure, signal return current came back through the conventional ground plane, or sometimes the power plane, or sometimes through adjacent metal line. Any metal could be return current path, and any metal could be return current path for power and signal. Any means they can change the return current path depending on frequencies and depending on terminations. So that is very typical part. When you are designing your circuit, in the circuit diagram, we never consider about the return current path. We assume that return current will come back anyway through the minimal impedance paths. But that's not true. It can go through any metal line, and because of the resonance and parasitics. So it is very difficult part of this. I think 99% of signal integrity and power integrity problem may be connected to the understanding of return current path and how you design the return current path. This is a odd case. There could be 1,000 different cases, and for the purpose of tutorial, I am showing you these 3 different cases. This is another case where let's assume that IO signal line is facing the power plane with the IO capacitor. Major capacitance is between your IO signal trace to the power plane. And for the case when we have a transition from a 0 to high level, this voltage level has to be same as this power level. That is because you have to connect this IO signal with the PMOS transistors. And then your decoupling capacitor will be, your power line will be connected to a signal trace as well as your power line, and then plus charge stored at the IO and minus charge stored to the signal line will be combined to make a heat. In this case, we're gonna have only loop on here, and because of that, no return current will be conducted at the conventional signal ground, and no current will be return current will be conducted at the conventional power ground. So this will be the summary of class right now. Signal return current path and signal and power return current path. That is the definition of digital ground. And number one, digital ground could be ground, power, or adjacent metal or charge. Any metal could be serving as a return current path, and that should be defined as digital ground. Number two, return current path could be line, trace, pins, planes, or via, or connector, and any metal could work as digital ground. In other words, return current path. And return current path will be depending on IO cap positions and your signal terminations. In the previous case, I was only considering the major capacitance between signal line and power and ground. But to make a complete analysis of return current path, we have to figure out terminations as well. But I'm not going to do that today. Also, return current path will change depending on charging or discharging process, whether you have positive transition or negative transitions. Sometimes you're gonna have overlap of return current path. Let's assume you have a single plane and it can serve both for signal return current path and both for power return current path. Then power noise will be transmitted to signal IO voltages. And that could be another type of noise coupling, and it could be resulting in a jitter increase or PSIJ, because power return current is generating some noise, and that is transferred to the IO signal because of the overlap of return current paths. There might be 1,000 return current paths, and we have to be careful about overlap of return current paths for each cases, and sometimes it could be a source of noise coupling. Number 6 message I would like to deliver to you is the return current path can switch metal planes. Sometimes return current path will conduct it through metal 1, but sometimes it will change the metal planes. And I'm probably at the second part of my class, and next week on Wednesday class, I'm going to go with many different cases. And also return current path is choosing their paths with minimal impedance depending on frequency ranges. And why do they change the return current path depending on frequency? Because they want to minimize the impedance depending on the frequency ranges. Because of parasitic, their impedance and resonance frequency will change. That's why we're going to have different return current path for different frequency ranges. And return current path sometimes goes through on-chip interconnection, on-chip ground, and sometimes on package ground, or sometimes on PCB ground, on passive ground. So usually in kilohertz range, return current path may go through at kilohertz range, and probably megahertz range, return current will go through the package, and probably 100 megahertz, it may go through on package interconnection. At the gigahertz range, return current may go through majorly through the ground metal planes inside chip. Sometimes you're gonna have common impedance noise because you are having same return current path for many different cases. If you have some impedance at the ground, and then it's gonna generate noise coupling. This is a short summary of class today and Wednesday. Let's continue the class now. To excite imaginations of students, I would like to discuss some cases where they are changing reference planes. That means return current path will change their metal planes. In other words, reference plane means ground, distal ground, and distal ground is not a single plane. Sometimes they are changing the return current plane. And I would like to give you a couple of cases to excite imaginations of our students. Let's assume that I/O signal line has a reference to the power plane and layer 2, and sometimes because of some reason, routability or something, let's assume that it is changing the reference to the signal layer 2, layer 3. When layer signal line is going through layer 2, their major capacitance will be between layer 1 to layer 3. Layer 1 is assigned to the power, and layer 4 is assigned to the ground. And through a via, this interconnection is connected to switch it to plane layer 3. There might be many cases. Because of that, we're gonna, in a case of transition from 0 to 1, signal current will be conducted through layer 2, and it's gonna go to the layer 3 through a via. And this current is actually supplied by our decoupling capacitors. And meanwhile, return current in this section is actually going through layer 4 because they have major capacitance here. And return current is actually, in this section, is going through the power plane of layer 1. And in this case, return current of power return current is going through the layer 4. That means somehow return current has to switch from layer 4 to layer 1. Again, it has to go to layer 4. Because power plane is usually has DC voltage and ground is 0 voltage, we cannot connect this return current from layer 4 to layer 1. And there should be certain capacitance, says. so that the return current has to change from layer 4 to layer 1 to layer 4 again. If you do not have proper capacitance that is connecting layer 1 and layer 4, your return current path will be disconnected. And if you have return current disconnection at this position, you're gonna have reflections. Impedance will be break and you're gonna have I diagram distortions and zero issues. My message here, number one here is that sometimes reference plane are being changed. We are assuming they will be conducted through some certain metals, but actually sometimes it is changing their return current path through the ground plane to power plane and power plane to ground plane again. Second message I would like to have here is that in order to help reference plane change, we may need some capacitance. It could be parasitic capacitance or decoupling capacitance and whatever. If you make a mistake in your digital interconnection systems, this could be true for chip level, package level, and PCB level. If you are not properly designed the return current path, you're gonna suffer impedance mismatching and multiple reflections. 종현이 한번 이 슬라이드 서머라이즈 한번 해보실래요?
네, 좋습니다. 그래서 이제 말씀해 주셨듯이 디지털 그라운드에 해당되는 그런 플레이 통일자 진행할 수 있다고 말씀해 주셨고요. 그리고 파워 프렌트가 IO 드라이버를 통해서 흐를 때 레이어 1이 어쩔 때는 리퍼런스 플레인이 들어갈 수도 있지만 기아를 통해서 아래로 내려가게 되면 또 레이어 4가 리퍼런스 플레인이 돼서 그라운드가 되는 상황을 설명해 주셨습니다. 레이어 4로 가면 이제 아래쪽에는 그라운드를 통해서 파워 그라운드를 통해서 리턴 그랜트가 흐르고 위에 또 반복되는 상황을 알겠습니다.
네, 잘 정리해 주셨고요. 중요한 포인트가 우리가 생각하는 그라운드하고 디지털 그라운드는 다르다는 거예요. 디지털 그라운드는 전류가 돌아오는 길인데 우리가 어떻게 트레이스를 라인을 설계하고 인터커넥션 설계하는 데 따라서 제각기 막 돌아온다. 그런데 그게 끊어진다는 거죠. 특히 비아 같은 경우. 그럴 때 디커플링 캐패시터 리턴 커런트 돌아오는 길을 시큐어 해주지 않으면 회로도에서는 정상적으로 동작하게 생겼는데 실질은 그렇게 동작하지 않는다. 회로도에는 이렇게 멀티레이어 이 구조를 이렇게 그리지 않으니까. 네, 그렇습니다. 그래서 회로도에서는 시그널 라인을 그렸지만 그 시그널 라인이 레이어 몇을 통과하느냐에 따라서 리턴 커런트 패스가 파워로 돌아올 수도 있고 그라운드로도 돌아올 수 있다. 네, 그렇게 되겠습니다. 그러니까 그때 다른 거죠. 그러니까 다 못 따지니까 운이 좋으면 잘 동작하고 운이 좋으면 잘 동작하고 안 하는 건데 이런 거를 다 컴플리트하게 볼 수 있어야 이제 회로 설계가 완성된다. 이 말이고 그런 거를 전 분야를 통틀어서 이제 시그널 인테그리티라고 하기도 하고 파워 EMI라고 하기도 합니다. Let's continue some more cases. We will move step by step. In this previous case, I was assuming that return current path is placed at the opposite part of PCB. Let's assume you have a PCB. This is a top view. You have IO driver, but decoupling capacitor is placed on here in multi-layer PCB. This is cross-sectional view, and this is top view. Your signal is going through here. That is the case of pages 3 and 1. So in this case, if you look at top view, power current will go through and return current will go through like that. They will face each other very close to each other to minimize the impedance. And signal line is going through the top of layer or layer 1, layer 3, something like that, and return current has to go through somewhere like that. And this is the actually cross-sectional view. But if you look at from the top view, what I'm saying is IO signal is routed on the opposite part of PCB, and the decoupling capacitor is placed behind on the backside of IC. So that's why we was able to isolate power return current and signal return current. They are isolated in terms of physical locations. But now I'm assuming that here, if we have on IC, this is, let's assume PCB, and let's assume we have IC and we have a signal line, but also we are assuming decoupling capacitor is placed on this side. Like many times we can have this kind of situation. Then our signal current will go through layer 1, and it will go to layer 3. And return current will go through layer 4, and some return current will go back at layer 1. Meanwhile, this capacitance has to charge off from the capacitance, decoupling capacitance, and it will be connected to the signal current through the PMOS transistors. And this return current has to go through, power return current has to go through somewhere else. I will not say very detailed right now, probably something like that. But my point here is that power current and signal return current has the same path. It's gonna make an overlap. Because we are relying on Maxwell equation, and that is linear equation. And linear equation means it's gonna have superposition principle. So in the same metal plane, layer 1 can serve as a power plane and return current path distal ground. Same plane can serve for both power current plane as well as distal return current path plane. And in this figure, I'm not trying to give you so details about the power return current path, but my message here is that depending on decoupling capacitor positions and depending on reference to signal line is traced on layers numbers, sometimes power current and your ground return current will be overlapped. For example, if you have certain impedance at the power network, and if you have resonances, let's assume you have resonances, because your return current path of ground is overlapped with this power resonance, it's gonna create the noise coupling issues. This is a little bit difficult part of the class, and yes, this is what it is. I believe that in the circuit theory book, at least 50% of their chapters should be assigned to ground, because the 50% of the actual circuit is ground circuit, because current has to come back. But actual circuit theory book doesn't care about the ground. That is their major mistakes, and that is why the actual system is not acting as you design in your circuit diagram. Second part of circuit theory is that they are assuming that we have constant voltage source, but that is not true, as we have discussed in this class. So now I would like to summarize my class today. Probably after the midterm exam, probably I have to continue my class a couple of more weeks, because I want to talk many more things about ground, and let's think about that. And if I want to extend my class even after the midterm, the final exam, I'm gonna send an email, and some student who is interested in this very difficult subject, they can continue to attend this class. Now, this is the summary of my class today. What is the direction of reference plane, reference design? Number one, you have to check every IOs to secure return current paths. For example, in your printed circuit board or inside your chip, let's assume you have 1,000 IOs like shown up here. Probably 90%, 99% may have very good return current paths, but some case you can make a mistake. In order to avoid those mistakes, you have to check every return current path for every IOs. It could be 1,000 or 10,000 or million. Maybe CAD or EDA tools can help us to check those return current paths. Let's assume that you have 1,000 decoupling capacitors. You have to check all the return current path of decoupling capacitors. And you have to check to avoid overlaps. If inevitably you have to overlap return current paths, you have to minimize the impedance so that you minimize the noise coupling between them. And I would like to say that return current is not conducted through a single path. It will change the path depending on frequencies. So you have to check these frequencies for many different frequency ranges: kilohertz range, megahertz range, 100 megahertz range, and gigahertz range, or 100 gigahertz range. You have to check at least 4 or 5 different paths. And when they are changing the return current paths, they are actually following the parasitics. If their parasitic inductance is too much, they will find the parasitic capacitance which will provide the low impedance return current path. So you have to be able to understand and estimate parasitic L and capacitance. If you have parasitic L and capacitance, it's going to have resonances. And of course, you have to minimize the impedance, and you have to avoid the resonances. And these subjects are at the list of class on Wednesday. And I would like to show you one more slide, then I would like a couple of more slides, and I would like to continue, conclude my presentations. We may have certain return current path through on chip. Let's assume you have IO driver and receiver at gigahertz range. So they have to go back through minimal impedance path. And to minimize the impedance, you have to minimize the inductance. That means you have to minimize the loop size of your return current path. Or sometimes, if necessary, you have to make an impedance match. So inside, when you are designing your chip, inside chip, you have to secure a return current path at this high frequency range, like a gigahertz. But please remember that inside chip, we cannot have complete metal plane. Usually we have to use the grid type of ground plane. So in order to minimize the inductance and to maintain, you have to properly design the signal line on the top of grid. That is very typical part of the interconnection design inside chip. But anyway, at really high frequencies, return current has to go through the on-chip digital ground. And usually that form of ground is in a form of grid type. So will be very, very difficult to maintain 50 ohm. And because of design rule, we cannot cover whole plane with metal inside chip. That's why we are using the grid type of the metal inside chip. And in certain way, we have on-chip interconnection has certain resistance. So at some frequency ranges, the ground will be connected to package ground, and return current has to go through the package substrate. And that could be a range from 100 megahertz to gigahertz. And at some case, return current, this signal current will go through the signal line, and return current has to go through the package, something like that. So on-chip ground and the package ground and the PCB ground has to be connected. And eventually, this computer system, your whole system will be grounded to chassis. And return current will go through the chassis. And that could be kilohertz range. So once again, my message here is that depending on frequency ranges, it will go through on-chip interconnection, or sometimes on-package interconnection, on PCB interconnection, on chassis interconnection. And you have to design your interconnection so that your impedance is under the certain ranges. But because of this path has capacitance and inductance, we're gonna have resonances, and you should be able to about these resonance frequencies, and we have to avoid the overlap of these resonances with the clock frequencies of your circuit, or you have to avoid the resonance of power plane network as well. This is the end of my class right now. I will continue this specific subject, more details on Wednesday class, probably after the final exam. And all of my message was summarized before, but I would like to say this thing again. When return current is disconnected, they have to be able to switch the return current path. And sometimes this parasitic capacitance will be really necessary. And sometimes on-chip parasitic capacitance, PCB parasitic capacitance, and chassis parasitic capacitance help. Sometimes decoupling capacitor helps. On Wednesday class, I'm gonna talk about how we will make the continuity of return current path, especially between the power plane and between the ground plane and power plane. And those will be the main subject of class on Wednesday. I would like to say this ground design, class of ground, is not a beauty. If we can explain something using a single beautiful equations or Maxwell equation, that is very beautiful theory. If we can show you some equations, and if we solve that equations using differential equations, it will become beauty. However, ground design, return current path design, and reference design is really depending on case by case. There will be 1,000 different cases. So it is not a beautiful theory. It requires a lot of imaginations. And sometimes this interconnection is the 3-dimensional, sometimes it is multi-layer stack, sometimes it is on-chip, sometimes it is packaged. There are many, many different cases. That's why this content is not shown up in the textbook. And my lecture today is not beautiful, but I'm sorry for that. But that is what it is. Thank you for your attention. See you Wednesday. I hope you enjoy and you appreciate this class. Thank you. Bye bye. 네, 그라운드가 이렇게 조금 지저분해요. 케이스 바이 케이스예요. 근데 프린시플은 하여튼 로 임피던스 패스를 찾아서 전류가 돌아오니까 그 길을 이해하고 연결시켜 줘야 돼요. 그렇지 않으면 회로가 회로도처럼 동작하지 않는다는 거. 예. 자기 마음대로 돌아오는 길, 그러니까 칩이든 패키징, 라우팅을 하고 플레인 디자인 한다고 할 때 꼭 다 따져봐야 되는 거죠. 따지 않으면 사고 치고 그러는 거죠. 네, 그런 면이 있겠습니다. 네, 여러분 중간고사 잘 보시고요. 수요일 또 뵙겠습니다. Thank you for your attention. Bye bye.